All right, welcome everyone. Today we're going to dive into one of the most fundamental concepts in all of physics, oscillations. Now, this isn't just about stuff that swings or vibrates. This is the hidden rhythm that governs, well, almost everything, from the tiniest atoms to the cosmic dance of planets and moons. Seriously, understanding oscillations is the key that unlocks the door to waves, sound, light, and even the wild world of quantum mechanics. So let's get into it.
So, to kick things off, here's a little puzzle for you. What single, elegant, physical rule do you think connects the vibration of a guitar string, the way a skyscraper sways in the wind, and even the orbits of Jupiter's moons? As we're about to see, all of these things, as different as they seem, are described by the exact same fundamental type of motion. It's a concept we call simple harmonic motion. And yeah, don't worry, we will definitely come back to how Jupiter's moons fit into this.
The answer, as you might have guessed, is oscillations. At its core, this is any repetitive back-and-forth motion around a central point, a point of equilibrium. For an engineer, learning how to control unwanted oscillations is absolutely critical. It can prevent catastrophic failures in things like bridges and buildings. And for a physicist, understanding them is essential because, really, oscillations are the building blocks of waves, which is how energy travels through the universe.
Now, all these real-world examples can get pretty complicated, right? You've got things like friction and air resistance mucking things up. So to really get a handle on them, physicists always start with an idealized model, a perfect repeating oscillation where no energy is lost. This fundamental blueprint is what we call simple harmonic motion, or SHM for short, and that's going to be our main focus today.
So, let's decode this blueprint. The beautiful thing about SHM is that this seemingly complex universal rhythm can be described with one single, incredibly elegant mathematical model. This one equation is the key to predicting pretty much everything about how a system in SHM will behave, from its position to its velocity at any point in time.
Okay, so at the very heart of simple harmonic motion is this idea of a restoring force. And it's exactly what it sounds like. It's a force that is always trying to pull or push the object back to its central equilibrium position. Just imagine stretching a spring. The farther you pull it, the stronger it pulls back, right? This direct proportionality, if you double the distance, you double the force. That is the single defining characteristic of SHM.
And here it is. This equation describes the position, which we call x, of the oscillator at any given time t. Let's break it down real quick. X sub m is the amplitude. That's just the farthest it gets from the center. The cosine function tells us the motion is wavy, tracing that classic up and down path over time. Inside the cosine, we've got omega. That's the angular frequency. It basically tells us how quickly the oscillations are happening, measured in radians per second. It's connected to the frequency f, which is cycles per second, by the simple relation omega equals 2 pi f. And finally, we have phi. Don't let that one intimidate you. It's just the phase constant. It tells us where the oscillator was in its cycle when we started the clock at t equals 0. And that's it. Those parameters completely define the motion.
Now we get to the true hallmark, the unique signature of SHM. This little equation, a equals negative omega squared x, tells us that the acceleration a is directly proportional to the displacement x, but, and this is key, in the opposite direction. That minus sign is everything. It means when the object is pushed to the right, its acceleration is to the left, always pointing it back home, back toward equilibrium. This is the mathematical soul of that restoring force we were just talking about.
This quote really nails that key relationship. Now, let's connect this to something you already know, Newton's second law, F equals ma. Well, if acceleration is proportional to negative displacement, then it must mean the net force is also proportional to negative displacement. You might recognize this as Hooke's law for springs, F equals negative kx. You see? The physics of the force is what creates the kinematics of the motion. They're two sides of the same coin.
This brings us to a great conceptual checkpoint. Based on what we've just covered, where in its cycle do you think the oscillator's acceleration is the absolute greatest? Think about that relationship between displacement and acceleration. The answer might not be what you'd first expect.
The maximum acceleration happens at the endpoints of the motion, the points of maximum displacement. This is where that restoring force is pulling or pushing the hardest. I know it sounds a little weird because the object's velocity is 0 for a split second as it turns around. But think about it. That's where the pull back to the center is at its absolute peak, causing the biggest possible change in velocity. And that, by definition, is maximum acceleration.
All of this constant pushing and pulling, is fueled by this absolutely beautiful and continuous exchange of energy. As the object oscillates, it's constantly trading one form of energy for another in a perfect dance that's governed by the principle of conservation.
So this oscillation is really just a dance between two types of energy. At the extreme endpoints, the object stops for an instant. Its speed is zero, so its kinetic energy, the energy of motion, is also zero. At that point, all of the system's energy is stored up as potential energy. Then, as the object gets pulled back toward the center, it speeds up, converting that stored potential energy into kinetic energy. Right when it zips through the middle, the equilibrium point, it's going at its maximum speed. So kinetic energy is at a peak and potential energy is zero. And then the cycle just reverses as it heads to the other side. And what this demonstrates is a true cornerstone of physics, the conservation of energy. In an ideal system, one with no friction or air resistance stealing energy away, the total mechanical energy, which is just the sum of the kinetic K and potential U, stays perfectly constant. The energy just keeps changing its outfit back and forth in a perfect closed loop.
So here's the really cool part. Once you recognize this blueprint, this pattern of restoring forces and energy exchange, you start to see it absolutely everywhere, in some really fascinating and sometimes really dangerous places. A simple pendulum is just a fantastic real-world example. Now, for small swings, its motion is a really good approximation of SHM. And check out this equation. It shows that its period, T, only depends on its length, L, and the local gravity, G. Notice what's missing? The mass. This is so counterintuitive, but it's why pendulums were revolutionary for timekeeping. A heavy pendulum bob and a light one will swing in perfect time as long as they have the same length. And this brings us back to Jupiter's moons. Imagine a moon in a perfect circular orbit. If you were to look at that orbit from the side, completely edge-on, what would you see? The moon would just look like it was moving back and forth, and that projected motion is perfect, simple harmonic motion. The very same math that describes a pendulum clock also describes the apparent motion of an orbiting moon. How cool is that?
This idea applies to pretty much everything, from a kid on a swing to a massive bridge or skyscraper. If you give any of these things a little nudge, they will oscillate back and forth at a very specific, built-in frequency. We call this their natural frequency, and it's determined by their physical makeup, things like mass and stiffness.
Now, this question is critically important for engineers and architects because the answer can literally be the difference between a building that stands and one that turns into a pile of rubble.
The phenomenon is called resonance, when an outside push, a driving frequency, perfectly matches the system's own natural frequency. The system soaks up energy from that push like a sponge. Every single push adds to the motion, and the amplitude, how far it swings, can grow and grow, sometimes to catastrophic levels. The best example is pushing a child on a swing. You have to time your pushes perfectly with the swing's natural rhythm to get them to go higher and higher. That's resonance.
And this is exactly what happened in Mexico City. The seismic waves from a distant earthquake just so happened to have a frequency that matched the natural frequency of mid-sized buildings. Those buildings started to resonate, swinging more and more violently until they collapsed, while taller and shorter buildings with different natural frequencies were left standing. It's a tragic but incredibly powerful example of resonance in the real world.
Okay, so to wrap things up, a few elegant principles describe this huge range of stuff happening in the world. It all starts with a simple restoring force, which leads to a predictable oscillation. That oscillation is a constant dance of energy. And when you push something at just the right frequency, you get the powerful phenomenon of resonance, which shapes everything from how a guitar makes sound to whether a skyscraper remains standing.
Ultimately, understanding oscillations is the first step toward understanding the very fabric of our reality: waves, sound, light, and even the fundamental principles of quantum mechanics. So it leaves us with one final thought to ponder. In a universe that's built on vibrations, what other secret rhythms are out there, just waiting to be discovered?